Today's lecture is the third lecture of deep foundations. In the in the first lecture, we just took an introduction for the types of piles and why do we use piles and how to simulate the behavior of the soil carrying the piles and so on. So this was in our first lecture. In the second lecture, we started to study the design of the first type of piles, which is piles with a diameter less than 60 centimeter, and we used the equations given in the Egyptian code for the design of piles. And we said a very important thing that what we are studying is not what the pile can carry. No, we are studying what the soil can carry the pile. The amount of load the soil can carry the pile. We usually say that this is what the pile can carry, but actually it is not. What we calculate using this equation, which is the load due to friction and the load due to end bearing, is not the load that the pile can carry. It's the load that the soil can carry from the pile. So this is a very important thing, because this necessitates that you should check what the pile can carry as a concrete section, because maybe the soil can carry more than what the pile, maybe the pile can carry less than what the soil can carry. So we have to, after we finish calculating the friction and the bearing and adding them together and getting from the ultimate the allowable load, then I have to calculate what the pile can carry as a concrete section and then take the minimum. So this was the second type, and we said that we have a very big equation, and this equation, long equation, and this equation has lots of parameters, and we've seen that these parameters we can get easily using fixed numbers, something like the C and phi. We can use the C and phi of the soil to get most of these parameters, and some other parameters are related to area, related to pressure, and so on. So we can calculate all of this. Once we calculate all of this, we can get the ultimate load of the pile. We divide the ultimate load. We'll just go below. This is how we calculated this. We said that there is load due to friction, load due to end bearing, and we said that friction will occur in every layer, but end bearing will occur only at the bottom layer. So because we had 3 layers here, so we had 4 items to add. For the first layer, friction; for the second layer, friction; for the third layer, friction and end bearing. So I calculate all of these, I add them together, I get the ultimate load that the soil can carry. I divide it by a factor of safety, given or not given, we can take it equal to 3. Then we get the allowable load. Then I have to check, this is what I was saying, the structural capacity of the pile. What the pile can carry as a concrete section. FCA multiplied by the area of the pile, I get a number. Here this number was 565, and what the soil can carry was 600 and something. Then it means that this was what we. So we take the smaller of them, and this is the next method is for piles that are more than 60 centimeters. Of course, 60 centimeter is a borderline. If I have a pile 60 centimeter, I can design it based on both. But anyway, we can say that here for more than or equal 60 centimeters, this method can be used. How can I do this or perform this analysis. To do this, I have to give you a background for the design of for this method. What is this background? Because this method depends on drawing charts and adding charts together. So I have to be sure that you know how to draw a chart and know how to add two charts together. So I'll just imagine that we are going to leave this lecture for a few minutes and go to this presentation. I have here a presentation for the friction of the frictional load of the pipe. As you know that there are two components for the load carried by the pipe or by the soil. What are these two components? We said the friction and the end bearing. Imagine that this curve shows the frictional load. How come? This is the load, and this is the settlement that happened according to this load. If we increase the load, imagine that you have a pile that is pure friction, only friction. You don't have end bearing, as if you have a gap below the pile, so the pile is free to move down, but it is not free to move because of the frictional forces all around. So if you add load, say 2000, you will have some settlement. If you increase this load 4,000, it will increase. 6,000, it will increase. Till you reach 7,000, you started to reach failure. How do you know that it is failure? Because once you put the 7,000, you will find that your pile started to fail. The settlement is increasing without increasing the load. So once I reached 7,000, I get this line. So it means that this is the failure load, because once I put this load, the pile disappeared, as if you are putting load on top of the pile, and suddenly you find that the pile disappeared in the ground. What happened? It's failure. This is a clear failure case. Sometimes failure is not that clear, but this is a very clear failure case. First of all, how can I draw this line, this curve? How many points do you need to draw this curve? Anybody can tell me? If I want to draw this line, this curve, and I don't have any information, and I will tell you, give me the information that I will need to draw this curve. You will tell me, you will give me just one point, this point. What are the x and y coordinates of this point? If you give me this point, I will just connect this point to the 0, 0, and I will go horizontally. So to draw the curve representing the friction, I need one point. What is this point? It is the load corresponding to failure and the start of the failure settlement. So it's when I added 7,000 kilonewton or ton, and then I got a settlement of 5. It started with 5 and it ended with 25. It did not stop. So if you give me this point, I can draw this friction line. Okay? Go to the other one. It's the end bearing. Imagine that you have a pile. It is not surrounded by soil, as if you are putting a lubricant between the pile and the soil. But below, it is completely resting on the soil. So what will happen? What will happen is that when you increase the load, there will be some settlement, increase the load, some settlement, and so on, till you reach, this time, if you look, you find that you reach a higher value. Here I said, as an example, 7,000, but here we reached 12,000. This is the logic. The logic is that the end bearing usually carries more than friction. It is easier for you to carry the bag from below rather than to hold your hand around the bag, because to hold your hand around the bag you'll get tired after a while because you have to grab it very hard. But if you are just carrying it from the bottom, this is easy. So end bearing is the easy load, so it can carry more. This is usually, but it depends on the layers. Suppose that you have very good layers all around the pile, and at the bottom you have very soft layer. So the end bearing will be it's nothing, but the main force will be what is all around. So this is the curve for the end bearing. The same. To draw this curve, I also need one point. What is this point? It is the load that corresponds to the failure of the end bearing and the start of the value of this failure. So when I added 12,000, there was a settlement of 15 millimeter, say, and it started and continued till the end of the test. So it means that this is another point. So if you give me this point and this point, then I will know the frictional load and the end bearing load. Okay, let's put them together to see. If you look at here, you will find that friction, of course, it did not reach a very high value like the end bearing, but it started earlier because this is the logic. If I am grabbing my bag, I'm putting my hand around it, I'm not letting it to settle even for millimeters. But once I reach failure, خلاص, this is the end of it. But end bearing, my hand may not be very tight, so it will not start carrying the load very quickly. But once the load pushes my hand below, then it will continue carrying the load till failure. So this is the normal shape of the friction and the end bearing, but as I said, this is for an ideal soil. In case of different layers, and this shape may be completely different, but this is usually what we expect from most soils. It means that the frictional load is this blue one, and the end bearing load is this red line. If I add them together, then this is exactly what the pile can carry, because the pile is a combination of friction and end bearing in the same time. So if I take these two curves, add them together, then I will get this green curve. To add them, I have to know numbers. If I want to add this, to get this point, this 11,000 is really the sum of the 7,000 plus this value, which is 4,000. So if I add this point plus this point and I put a point here, then this is the summation for these two curves at this location. And then I go to this point. Here is 7,000, here is 12,000. I add them together, I get 19,000. So these 19,000 is the sum of these 2 points, and so on. Any 2 points, I add them to get the sum. Then I connect all points together to get what I need. But here, just to save time in solving the problem, imagine that you have these 3 points. Is it important for me to get this point? No, because if I have this point and I know that it is connected to the 0, 0, is it important to get the value here? No. So I should be selective in choosing which points to calculate. Don't waste your time in calculating points. Imagine that you are going to calculate a point here. You will going to add this value and this value to get this value. Why? I have a point at this here and a point there, so I don't need. So really, when you come to calculating this summation curve, you are going to calculate 2 points, only 2 points. One corresponding to the failure load of the friction, and one corresponding to the failure load of the end bearing. That's all. Don't calculate more than that. So to draw the curve for the friction, I need 1 point. To draw the curve for the end bearing, I need 1 point. To draw the collective curve, I need 2 points, corresponding to the 2 points that I have calculated before. Okay? This is very important. Once you reach this green curve, we said that this green curve is the summation of the other 2 curves. So don't waste your time. Delete the other 2 curves. You don't need them. You only need this green curve because this is the actual behavior of the pile. The pile, it is a combination of friction and end bearing. So this is the curve showing the combination of the friction and end bearing. I don't need a curve for end bearing alone, and I don't need a curve for friction alone. Don't confuse yourself. Just imagine that you don't see them. Okay, I have here a curve. By the way, this curve resembles to what? Do you know what is a loading curve for a pile? Any one of you has heard before a pile load test? If I have, I need to perform. Sometimes you go to any site, you find that there is a huge bulk of rocks and stones or concrete blocks all over each other. And if you ask what is this, they will tell you that we are testing the load of a pile. So in pile load test, we subject the pile to very high load, and we increase the load bit by bit, and each time we increase the load, we measure the settlement till the pile fails. In this case, what is carrying the load of the pile? The friction is working and the end bearing is working simultaneously. Both are working together. I'm not having a chart for this and a chart for this. Is the combined chart for them. So this combined chart that I have calculated from these two is really similar in principle to the pile load test result. So it is as if this is a pile load test. So in this case, of course, a pile load test will not be straight lines. It will be a curve, a pure curve. But once the pile reaches the failure load, I will find that more or less I will have a line which is similar to this one. Why I will have a line? Because it's failure. It means that without adding additional loads, I'm having settlement. So this is the failure load of the combined friction and end bearing. Here, this was the failure load of friction. Here, this was the failure load of end bearing. And here, this is the failure load of the combined effect of end bearing and friction. So this is here the combined effect, which is how much? 19,000. So this is the ultimate load that the pile can carry. If I need the allowable load, how to get the allowable from the ultimate? I have ultimate load, which is the maximum load carried by the pile. After this load, the pile will fail. I tell you, give me the allowable. How to reach the allowable from the ultimate? Factor of safety. So I will just take this 19,000, divide this value by a factor of safety, 2.5, 3, whatever the code tell you. So I will divide this value by a factor of safety to get this dotted line. So it means that this dotted line is the allowable load of the pipe. So this is the first check that we usually do. The second check, what is it? The value of the settlement. Suppose if you go with this load, cut this curve in a point, this is 6,300, and so I go from here, I cut this point, this curve in a point, I get the corresponding settlement. I will find that the corresponding settlement is more than 2.5. It is not allowed, because from my knowledge of the design of the footings, I need, from the requirement of the structural engineer, he tells me that your foundation settlement should not exceed 2.5 centimeter. So it's another check that I should perform. I will come from this side, from here, take 2.5 centimeters, go up, cut the curve in a point, then go horizontally to get this load, which is 5,500. So I have now two cases. The load corresponding to the maximum settlement is 5,500. And the load corresponding to the ultimate load that the soil can carry is 6,333. Which one will be the governing in my case? The minimum, which is 5,500. So if I take this value, then this value is the value that the soil can carry. But as I said at the beginning, I still have another check. Do you remember what it was? All of this is speaking about the soil. We did not speak about the pile. I will have to check the pile as a concrete section. This is another thing you do after you finish your solving of the problem. You can, in just one line, you calculate what can the pile carry and compare them together. So from here, you take a factor of safety and get a value, and from 2.5 centimeter settlement, you get a value. Compare this value to this value, take the minimum of them, and I add, compare it to what the pile can carry as a concrete section, and take the minimum of them. Okay? Now we return back to our lecture. This is the Egyptian code. The Egyptian code tell you that this is how can you solve a problem like this. As we said, to draw the curve for the friction and for the end bearing, for the friction, and the curve for the end bearing, I need 2 points. Only 2 points, 1 point for each chart. So the code told me, or stated that to get this point A, or to get this point B, I will need 2 coordinates for each. For A, I will need this point and another point here, and for B, I need this point and another point here. Let's get first the values corresponding to the settlement for both. So I need here that you would give me SF, which is the settlement corresponding to the frictional failure, and here SB, the settlement corresponding to the failure of the bearing or the end bearing. So the code stated that SF, it may be taken 5 to 10 millimeters or 1% of the diameter. If I have a pile 60 centimeters, 70 centimeters, here we said that it is more than 60, 70 centimeters. So 70 centimeters means that I will have 1% of the 70 centimeters is 7 millimeters. So the 7 millimeter is between 5 to 10. Then I can take the 7 millimeters, it's okay. If I get a diameter that is very big, so it gave me here, instead of instead of giving me 7 millimeter, it gave me 15 millimeter, then I will take the maximum here, which is 10, because they said that it is between 5 and 10. So now I can assume a value for SF. Now I go to SB. For SB, they gave me two options depending on the type of the soil. Is it cohesionless or cohesive? Is it pure sand or pure clay? Usually it is not pure sand and it is not pure clay, so it is something in between. So it depends on my judgment to take a number in between. If it is cohesionless, which is pure sand, then SB will be 15 centimeter. If it is cohesive, then it will be 5% of the diameter. Then I will, depending on the type of the soil, I can, it's either use this, use that, or use number in between if I have something, combination of two types of soil. So now I got these two coordinates, the settlement coordinates of the failure points. I need the failure loads. Here I need this ultimate base resistance, and this I need ultimate skin friction, because this is for the frictional load, so that is the ultimate skin friction, and this is the ultimate base resistance for the end bearing. The code also gave me the they both depends on the type of the soil. For cohesive soil, if you want to calculate the ultimate skin, this point, it's either you go to table 411 or 410. 411 for cohesive soil, 410 for cohesionless soil. And for the other case, for the other point, ultimate base resistance, you have two other tables or two other charts. No, they are tables, 4.9 and 4.8. One for cohesive and one for cohesionless. The same. I will just go to these tables. This is the table 4.8. This is the table 4.9. This is the table 4.10. This is the table 4.11. These are the four tables that I will need. Just what is the value of the, say here, the maximum frictional stress? It depends on what is the C value of the soil. If your C value is 0, then it is 0. If your C value is so and so on. For each table, you just go here. It depends on the number of blows, SPT value. Based on your SPT value at the depth, at the required depth. Of course, here when I say at the required depth, if I have a pile 25 centimeters and I need to calculate the failure due to bearing, so it will happen at the tip of at the bottom of the pile. So I find that the pile is at a depth of 25. I go to this table here from 20 to 30. Then this is the this 20 to 30 is the number of blows. I confused. This is the number of blows. So it depends on the number of blows at the layer that you are studying. So if the number of blows is between so and so, then you get a value. You will see this in an example with numbers so that you know everything. We'll take the example. I have a pile. It is 50 meters from ground level. This is very important. When I say a pile, 50 meters from ground level, this is not the pile length, because the pile length starts from the bottom of the pile cap. So the pile cap is at a depth of, here say it is, I don't see this number, maybe it is 2 meters or 1. Then we'll see it. You will find it while solving this. Okay, so here to solve this problem, then I will have to just subtract from the 50 this value, which is it may be 1 meter, 2 meters. We'll check in the example. This is this is what we are going to use to solve this problem, because if the pile diameter is 1.2, so it is more than 60, then I will have to use this approach. To use this approach, then I will have to calculate this point, and this point, and this point. So I have to calculate 4 values. Here, how we can calculate the 4 values? To get SP and ultimate base resistance. So this is the first point. SB, if I go to the curve, to the previous slides, I will find that SB in this case will be 15 centimeters. I go to the ultimate base resistance, I go to the table, I will get the number here, which is the ultimate base resistance. I multiply it by the diameter, the area of the pile to get the load. So this is the first point. Then I will have, this is for SB and the ultimate base resistance. This is for SF and the ultimate skin friction. Here the SF was 1 centimeter, and of course, and the same I go to the table. Hey, here it was table 410, and I get the values. Of course, in the exam you will not have these charts. You will just get a direct value. I will tell you that the value of this is so and so. Then you can use it and continue solving the problem. What is this? If you go to this table, which is 410, let's go to 410. This is 411, this is 410. You will find that depending on the number of blows, he is giving me a value for the maximum frictional stress, but it is not one value. He said that from 0 to 2, it is 0, from 2 to 7 it is another one, or sorry, say from 2 to 10 it's another value, and from 10 and more this is another value. So that's why you will find here in this that from 0 to 2 it was 0, from depth 0 to 2 it was 0. No, not considering the skin friction. Even if the pile was starting from the ground surface, I'm ignoring the first 2 meters. Then I will go here. So this number is 2. This is the number that we did not see. It is 2 meters. The depth of the footing is 2 meters. Then from 2 to 10, he gave me a value of 60, a stress of 60. And from 10 below, it was 100. So to calculate the whole frictional stress, then I will have to multiply this 60 by this length and this 100 by this length and add them together to get the full frictional load carried by the pile. It is easy and we can calculate. Here in the problem, he told me ignore the last 5 meters of the pile. It was given, so that's here he said that effective frictional length is 45. Ignore last 5 meters. In this problem, he does not want to depend on the last 5 meters in friction. This is the type of soil. This is the case. It's not the case in any problem. Yani, you should not ignore it in each problem. But in this problem, it was required to ignore it. So that's why the last 5 meters, I did not go to 50 meters. I just went down to 45 meters because the last 5 are ignored. So based on this, now I could calculate this first point, which is SF with the ultimate skin friction, and I have this point SB with the ultimate base resistance. So I have this point and this point. So if I have this point and this point, then I can draw these 2 charts. And if I can draw these 2 charts, then I can use the information I got here and add 2 charts together. So this is what you are going to do here. You are just going to take these values. Of course, the shape is a little bit complicated because it's real life, not an illustration. So this is the curve for the base resistance. So this is the point that I got for the base resistance. It was 15. with say 4,000. So I have this point, I connect it to the 0, 0, and I go horizontally. This green is for the friction. This is the point that I got. I connect it to the 0, 0, and I go horizontally. So I have two charts now. The friction, which is the green one, and the base or the end bearing, which is the red one. I add them together to get the green, to get the blue curve. So once I add them together, then I will use the blue curve. So from this blue curve, I know that this is the ultimate. It was something like 19,000. So this 19,000, I divided by a factor of safety, which is given in this problem to be equal to 2. I divided by 2 to get the allowable. And in the same time, I will go with the settlement value, which is 2.5. I go up to meet the blue curve and then go horizontally to get the corresponding load. I compare both loads to get the minimum. Once I get the minimum, then this is the load that is carried by the soil to carry the pile. Then I will need to add, whether it is given in this problem or not, check for the pile as a concrete section. If you know the area of the pile, then you can, and you know FCU of the concrete, then you can calculate the pile as a concrete section, compare it to the minimum from these two values. This is for the allowable settlement, and this is for the allowable coming from the ultimate. Choose the minimum, compare it to the concrete section to get the value that the red one is for the end bearing. Yes, as I told you, this curve is an illustration. So it takes everything into consideration. But this value is coming from from an experiment. So it means that soil may be very good in friction, but very weak in end bearing. So this is the shape of the curve. That's why it is a little bit distorted. But you have, for illustration, I give you this shape. But when I give you an example, I should give you an example that a little bit confused, so that in case you in real life you have different values, you can understand that this soil is not ideal. Every time it depends on the values of the soil layering you have, the parameters of the. Then the allowable geotechnical, when I say geotechnical capacity, it means due to the soil. Geo means soil. So when I tell you what is the geotechnical capacity of the soil, of the pile, it does not mean what the pile can carry, but what the soil can carry. So geotechnical capacity is 9,422. As I said, we check the pile as the structural capacity of the pile. Then I multiply FCA, not FCU. I said FCU, it was wrong. It is FCA. I multiply FCA by the area of the pile to get a load. So it is 5,000. And so the soil can carry 9,000, but the pile can only carry 5,000, so this will be the pile capacity, which is this one. There is another type, which is the dynamic formula, but I will stop here for this part of the lecture, because now we took, first in the previous lecture we took the design of a pile that is less than 60. Now we took a pile that is more than 60, so now you can design the full spectrum of diameters. Later we are going to take another method that is applicable for all types. It does not have a limitation for the diameter, but it has a limitation for another thing that we will discuss later. So this ends our part of this lecture. Thank you.